It's kind of like that. Doesn't it? Yeah. The way I'm thinking about it is like the way of solving the idea. Thank you. Okay,
Cool.
we start again.
Yeah, sounds good. So something which I was going to mention was that although the synchron algorithm doesn't depend on the dimension of your state, it just depends on the cost matrix. So if the cost entries are, the cost entries can be highly dimensional, and it wouldn't affect the complexity of the synchron algorithm, only in actually computing the cost matrix, which is a one-off thing. The dimension comes in whereby if you have taken an empirical measure of some continuous space, like to sample some continuous measure twice for two different measures, complete the synchron, complete the transport between the two, and use that to approximate the high dimensional continuous measure transport, then that scales really badly. So that's I couldn't find the exact rates, but it's like exponential d or something, minus d, yeah. No, minus 1/d. But yeah, anyway, so I'm going to talk about an application which I think hopefully will make things a bit more tangible. So hopefully everyone's kind of familiar with state-space models and the general probabilistic model whereby you have some unobserved states which evolve through time and some transition. I'm going to use P and F for the transition interchangeably and the observation P and G, and they're parameterized by some theta. So these are used all over the place. So in epidemiology, so say the number of people who are infected with something you don't really observe, so that's your X, but the number of people who test positive or die or something at Y, you do observe. And so maybe you're interested in inferring the number of people who are actually infected, the X's through time, or you're interested in learning the parameters theta, which could be like your transmission rates or something like this. Autonomous driving, again, the Y is the cameras around your car, what they can see on the road, and the X could be the location in the road given the camera images. Say for in tunnels where GPS isn't good enough, basically. GPS is accurate to a meter or two, but autonomous driving, meter or two, could do a lot of damage. Or the GPS goes off or something like this. So I know I actually presented this work at Waymo, and they use particle filtering extensively in their autonomous driving cars. Yeah, and I think people used it for the COVID app. It didn't really work very well, but they remember the NHS COVID app. It was, so one of our most former students was leading this. So yeah, there's two objectives: is to infer the unobserved states through time, given the observations, and learn the dynamics. So either the observation dynamics, the theta here, so the actual parameters of your transition, and observation models. So in the likelihoods is tractable, and there's some nice guarantees behind this. So the log likelihood isn't unbiased, but it's as you increase the number. Oh, this is the log likelihood. So I'm going to start this in the non-particle setting. So this is just the regular state space model. The problem is these integrals aren't tractable. So particle filtering essentially is approximating a lot of these integrals with particles and importance sampling. But this recursion gives you a likelihood, and the particle equivalent essentially is doing the same thing. So proposal, if I'm going to send these slides around as well, if people are writing notes, I'm happy to send. But please pause me if you're writing something. So the particle version of filtering, if you like, follows the same recursion, proposing some samples, weighting them by some importance weights, and then reset. What's different from the particle setting is that you have this ingredient resampling, which is essentially like a birth-death process, killing off some bad samples with low weights and keeping the good ones with high weights. And this is quite important to prevent degeneracy. So I guess this is that's 101. And so this is actually an experiment where you have essentially the state is your location in the map, and the observation is the image, and trying to find out where you are in the map given the observations, which are slightly noisy. This is the kind of thing people do. Okay, so again, the log likelihood for general model with this integral is the top, which is the what people hope to get. Using a particle estimate, you can get something which is unbiased in the likelihood, but not the log likelihood, but asymptotically it goes to the correct log likelihood. So great, you know, you have a likelihood, and like the inferring the hidden states is quite trivial. You just run this recursion through time to work out the hidden state given the observations before it. But then, if you want to learn the transition dynamics, the actual parameters, one way of doing this is like maximum likelihood on this function. The problem is, and people have tried this a bunch of times, so like, yeah, lots of papers basically. The problem with all this is that the resampling step is non-differentiable. So say you want to learn maximum likelihood via gradient descent. So okay, for convex settings, this is not ideal. But say you have some big parameterized model for your transitions, then it's not too much of a concern. Or even for a convex setting, you want to learn your Gaussian, say in the Gaussian setting, because there's better algorithms, but perhaps you want to learn the transition matrix through gradient descent. So if you recall here, we have a simulated likelihood, which we can take gradients through up to ignoring the resampling step. This is not differentiable. And we show that actually the true gradient looks like this. If you take the limits of your particle estimate, ignoring the resampling, you get something very close to the true gradient. If you look, the only difference is in this term here. So this means for very large time series, if you ignore the gradient term with respect to the resampling part, you'll have some errors if your time series is very long. And it's error in the gradient. So if you're doing parameter updates and you have a biased gradient, there's no guarantees that your parameters will, or the gradient descent will even converge. Or at least not that I'm aware of. But if you have bias in your likelihood, then your parameters should be reasonable. So yeah. So this is kind of motivating a way to do differentiable resampling, basically. So also for the Gaussian setting, so a linear Gaussian state space model, the likelihood looks a bit like this, a nice surface from a Kalman filter. So here the axes are the parameters, theta 1, theta 2, I don't think it's labeled. The particle filter likelihood is a mess, right? So it's extremely jumpy. Even this is the same random seed, it will still be jumpy if you change the parameters, because resampling will change the importance weights, and so resampling will create discontinuities as you go through. So it's very jumpy, and this is, I guess, kind of well documented. So if you try to run optimization on this, it won't look very nice. Oh yeah, there's no animation, but essentially resampling can be thought of as creating a coupling between your weighted and unweighted particles. So say in the multinomial case, where you simply hit say these are particles which are uniformly weighted, and these are weighted particles with the importance weights. Essentially for each particle, you sample uniformly across the row, and it's the same for each one. And the row entries are proportional to the importance weights. So this creates discontinuities because, so this particle, which may be very close, so these are the same particles but different weights, the same atoms but different weights. So this and this will be very close because they're the same atoms but different weights. So you think most of the weight here, if you want to do an unbiased resampling, you'd hope that you keep this atom close to itself or not move very much. So that's the kind of the basic gist. Multinomial doesn't ignore it's completely blind to the location of your atoms when you're resampling, so it creates these big jumps. So particles move, like, I guess, quite significantly. One way of doing this instead is to create a better coupling. So any coupling will be unbiased. I'm going to jump forward a bit and then back, but I thought I had another slide. Oh, never mind. So any coupling will be unbiased if you sample across the rows of the coupling. But the problem is then, even if you're sampling, it will still be discontinuous, like you have discontinuities. The optimal transport coupling will be very sparse, so it will concentrate on the diagonal, where the particles are the same and they're ordered in the same correct way. This means rather than sampling each particle, take the average across the rows of the particles. So this is the average or the barycentric projection.
Can I ask you what's alpha beta? Yeah.
Oh, so alpha is the say you have a proposal particles for each time step. This is the uniformly weighted version of the particles, and beta is a weighted version according to the importance weights.
Okay.
So yeah, sorry, I had another slide, but I think I missed it. So yeah, this is the basic gist. So resampling essentially is going from weighted to unweighted.
Yeah.
Here we're trying to recreate unweightedness, but using in a differentiable way. So essentially, if you have this sparse coupling, like I said, if you sample across the rows, it'll be unbiased and almost smooth, but not quite. If you take the average, it will introduce a bias because now, or introduce a bias for non-linear functions, but it will be differentiable. And you can actually show, so we've got some quantitative convergence rates on how close or how the bias will disappear asymptotically as n goes to infinity, and you can control this quite well. And as your particle filter goes to time, if you're applying resampling every time step, yeah, it can be you can control how close your ultimate likelihood is to the true likelihood of the particle filter with multinomial resampling. So what does all that mean? It means if you use optimal transport here, you can take a gradient through your likelihood all the way through your particle filter to learn the transition dynamics. So say for, I don't know, some COVID example, say you want to have some very complicated dynamics, which you don't want to use an expert and you just use a big neural network which takes in, I don't know, people's mobile phone tracking data and all sorts of stuff. Then you can learn the parameters of that neural network by taking a gradient through the likelihood. It may not give you reasonable results, but you can do it. So that's kind of hopefully a reasonable motivation for how we can embed an optimal transport into so a multi-caliber procedure essentially, and a sort of neural network procedure as well. And it benefits from a few things. One, there's nice theoretical results. And it's quite practical as well. So it's yeah, it's kind of a nice mixture of stats, sampling, machine learning, transport. So it's I guess it's a nice mixture of everything. Okay.
With a bias gradients, I mean asymptotic and biased.
Yeah, asymptotic. Oh no, this is unbiased gradients. The gradients, so as in the likelihood is biased, but the gradient of the biased likelihood is unbiased.
Okay. Yeah, I understand.
Yeah. So I think that's in contrast to a unbiased likelihood but biased gradients, which at least this way we know that the likelihood which is biased but is asymptotically unbiased. And we have convergence rates, but they're really, really bad and have a lot of assumptions, so it's not included. And so if you look at the particle filter with this ensemble transform, this is the curve on the right, and it's nice and smooth, so it kind of works, which is nice. Like it's not exactly the same, but it's very close, and it has roughly the same optimal. Okay, so that was the synchron part, and now I'm going to go into the Schrodinger bridge part. So the Schrodinger bridge is essentially it's a regularized optimal transport problem, but on the path space of diffusions rather than on couplings. So I'll go into some detail. Oh, so what I'm going to include is the Schrodinger bridge and its links to optimal transport, IPF, the iterative proportional fitting, which is the equivalent of synchron, but in continuous state space. How to approximate this with theoretical guarantees with diffusion models and time reversals of diffusions. And yeah, how to use that to solve the IPF and solve transport problems in high dimension. And we show that the problem is with this is no ground truth, but for high dimensional Gaussians, it seems to get the correct couplings. And it can be used for very high dimensional optimal transport problems. So in the space of images, and it seems to work. Okay, but there's been a lot of recent work extending this to conditional settings from to a setting without IPF or without sync-on, but I'm not going to include that because these were just last week or two. Okay, so what is the actual Schrodinger bridge problem? So originally it was formulated by Erwin Schrodinger for some gases moving in space. And essentially, say you have some reference diffusion, so Brownian motion or something, here denoted P, indexed by time. You want to find, say you observe, I think one way of explaining this is, say you observe some particles moving at time 0, or so observe some particles at time 0 in a room, you turn off the lights, then at time t, you turn the light back on, and you see the particles again. What's the most likely trajectory of the particles if you only observe the two end states? And one way of doing this is looking at finding the closest trajectory, pi, to your reference trajectory, p, in terms of KL, subject to the constraints that the marginals at time t are the same. So P0 equals P data. Okay, I've called it P data and P prior, but P0 is P data and PT is P prior. So this is the problem. I believe yesterday people talked, there's another formulation of this problem in terms of fluid dynamics and energy. I'm not going to go into much detail about that because it's not as tractable to solve. So it doesn't have the same connection to sync-on and everything. But people can solve it by just running a diffusion and taking a gradient all the way through the diffusion when parameterizing with a neural network.
The diffusions that you are considering are any diffusion or absence of diffusion?
So this works with any diffusion, but there's a close connection between optimal transport if you use the Brownian motion reference measure.
Okay, so the diffusions are Brownian motion?
So the P is a Brownian motion,
okay.
or an on-site Lundbeck process. So those are the two typical ones people use. I think there are other use cases for physics whereby you probably have a more informed reference diffusion. I just haven't really found anyone who can give me some data and yeah, some problems to solve.
Some of the linearity of the diffusion is
it's beneficial. Yeah, I guess we kind of came up with this for generative modeling use cases. So it didn't really matter what the reference diffusion was, as long as it was something which converged with something we know. So these are I guess I'll talk about it a bit later, but essentially what we want is that your reference diffusion converges in time t to something which is tractable. And so for a Brownian motion on on-site Lundbeck process, you can choose that target distribution. Oh yeah, no worries.
Set up, especially for marginals, like pi 0 is the data type higher.
Yeah, so actually this should be, instead of P data, call it P0 and call P P prior PT. So I change this now actually. So the use of prior is a bit it would make more sense a bit later, but people use prior here a bit loosely. It's not an Bayesian setting.
Okay.
Well, actually, people have used it in a Bayesian setting, but in this case, we're not using it in a Bayesian setting.
here, I guess it's PT, right?
So yeah, if you consider your updates, you start with it's in the reverse direction. So people typically start sampling from PT, which is the known as the prior, and if you run your diffusion, you'd be able to sample from P0.
Which is the thing that was intractable.
Yeah, exactly, which is like the data basically. So say you have a P0 is a complex distribution of images. You can diffuse the images into a Gaussian pixel-wise or independently and sample from that Gaussian, but then reverse the diffusion to sample from your data. Yeah. Okay, so this is the general problem setup. And why do you want to do this? Yeah. So again, for sampling, if oh, it's not really sampling, generating. I guess people can use sampling. If your optimal is like coupling, the whole path is available. You can sample from the data if you like by sampling from the prior, and sequentially sampling your diffusion using a discretization of your choice, backwards in time. So this is for generating stuff, but it can also be used for trajectory inference. So if you have an informative reference diffusion, then you might be, say, in a physical situation, you might be interested in the actual trajectory of your dynamics, basically. So an example of this would be bird migration on a sphere. Say you want to infer where the birds are going based on where they observed. People use it for single cell dynamics, which I don't really know much about. And robotic interpolation. So you have a robot and you have its data sets of it holding a cup while standing up and sitting down. You want to know the optimal way or the closest way for it to move between standing up and sitting down, this kind of thing. Okay, so connection to optimal transport. So the dynamic Schrodinger bridge formulation is on the whole path space of the diffusion from time 0 to time t. The static problem is ignoring the middle part and just looking at the end parts. So this is actually an optimal transport problem. So the way to see this is that the KL can be decomposed into the marginals at time 0 and time t jointly between your thing you want to learn and your reference that you are given, and the intermediary path between the two. If the coupling at the endpoints was known, then this, so saying the Brownian motion with the reference, say the reference was a Brownian motion, and the two endpoints was known, so we know what the coupling is. Then this is just a case of sampling from the Brownian bridge. So the optimal, you can set that to be essentially 0 basically, and you can learn directly the coupling. So again, this is a KL minimization. Doesn't really look like a regularized optimal transport. So we want to show that essentially, if you do some maths, the top line will look like the second line, where H is this entropic regularization term. And the ground cost here is your distribution. So this is N, so it should be T, sorry, of the conditional distribution, or the log conditional density is your ground cost. So it's the same as what we talked about before in terms of synchron, that your exponential C, so this part here, looks an awful lot of minus here. The ground cost can be obtained by taking the negative log of the C. And I'll show how you get this.
Ask you a question.
Yeah.
So this minimization problem, does it change if you vary T, capital T? So it's kind of a tuning parameter, right? Capital T.
Yeah. So it's how long you run your diffusion for.
Do you know if the reflection regardless?
So it's a trade-off between the complexity of your. So if you have a very long T, it turns out your regularization would be quite high, which is not ideal for some settings. Also, if you want to learn the reverse diffusion, you have to train a diffusion along a lot more steps, so it's a bit more complicated. So yeah, these are the kind of trade-offs.
The solution depends on these parameters.
Yeah, exactly. Yeah. So I guess another thing is that, so essentially we're learning a reverse diffusion, or a diffusion close to another diffusion, with fixed endpoints or fixed distributions. The prior or the reference diffusion may only converge at infinity, but here we're coming up with a close reference where the marginals are fixed. So it's a bit more challenging. Essentially, it's looking at finite time, continuous state, MCMC, basically. Okay, so I think I've got the calculation. Yeah. Sorry, it's a bit messy. Essentially, if you look at the static program, a static KL minimization, take the KL, expand it, so actually compute it on the coupling, you get this, swap H of the entropy term, extract that, and you get the negative log of the coupling. Yeah.
Sorry, just a question. Keep doing this. What does it stand for?
So say you have a your diffusion times 0 times t, just looks like this.
Or is it that the whole path?
So pi is the whole path,
Okay.
and then pi 0 is here, pi t, and then pi 0 t is just this is.
Oh, the two marginal.
Yeah, imagine exactly. Yeah. So if you can decompose this, I might refer to this later. Is that pi equals pi 0 t pi. You have a line 0 to, and that's like the path in between 0 and t.
Okay.
Okay. So basically, if you set this for long enough, you realize this is true. And because the pi 0 is fixed in the argument, just the argument over the coupling, not the marginal, then your optimally your KL, the minimum of the KL is the same as the min of this, where this is the ground cost and this is the regularization. So what does this look like for Brownian motion? It's just a L2 cost, so this recovers your Wettstein regularized Wettstein distance. The sigma here is the variance or the standard deviation of your terminal distribution. So the pi, again it should be t, pi pt given 0 will be, or the negative log will be xn minus x0 divided by sigma squared, and just times everything by sigma squared.
What's the superscript S here?
So this is the static problem. Sorry, guys. So I think the dynamic problem, the whole path, will solve the static problem, and the static problem is the optimal transport problem. So by solving the dynamic problem, you solve the optimal transport. And yes, as you decrease your sigma, you get the unregularized case. If you use an Onstein-Umbeck process, your ground cost will be slightly different. And depending on your reference diffusion, you get a different optimal transport ground cost. So if you have a really informative, like if you know what your ground cost should be in terms of a diffusion, then you can solve the transport for that using this mechanism or this framework. So this is what answering your question about how to choose the reference diffusion. It's based on the ground cost or the exponential or the negative of the ground cost. Okay, so how is this actually solved? So it's always great, and it's nice to formulate these problems. So there's again something called the IPF, which is equivalent to Synchron, but in continuous, a more general version of Synchron. So I think the first reference of this was Robert Forte, which coincidentally is my supervisor's 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 supervisor. So it's a nice kind of hierarchy. And what this states is that you can find the optimal diffusion close to the original one by solving these half bridges, which are essentially these KL minimizations with a fixed margin at each point. So if you recall, this is exactly the Bregman projections that we talked about for Synchron, but on the path, on the coupling of the path, not just the coupling on the 2 points. So I'll talk about, I won't provide the proof of why this works, but I'll provide the theorem that shows that it works. So yeah, this is what we want to solve, this KL minimization at each time point. Again, this is non-trivial for like high dimensional complex paths and everything. So it turns out that each KL minimization can be computed in terms of the time reversal of a diffusion. So if you take a reference diffusion starting at pi 0 or pi t and reverse that, you get the closest, but with a fixed marginal. And I don't find this diagram super useful, but you see this pop up a lot in every paper on Schrodinger bridges, I think. Essentially, you're doing projections onto the two marginals. This is what that's trying to show. So this is the connection between Sinkhorn and Schrodinger bridge, or the IPF. They're meant to be the marginals in the space of things. So you somehow want your, so the pi here is the marginals, the pi here is the whole process. You somehow want it to intersect the marginals. But yeah, I don't think it's super clear to me. Okay. So why does it converge, or does it converge? And yes, it is converge under some mild conditions that essentially your transport is finite, and your priors and your marginal distributions have positive density. So it does work, and it has, I guess, a linear convergence. Basically, we have superlinear convergence. I'm not going to go into a lot of detail into this, but I'm just going to go through the practical side of what this actually involves. So when I mentioned that each iteration is each KL minimization is a time reversal of a diffusion, this is the kind of picture I have in my mind, and I'll talk about how to actually solve the time reversal after this. But say the forward process is a Brownian motion, starting from this S curve at the top left over there, and eventually this distribution is just two-dimensional points on shaped in an S. If you add enough noise to the Brownian motion, you get a noisy S curve, which is not fully converged yet to a Gaussian. And if you reverse that time that diffusion, so you perform the time reversal starting from a Gaussian, reverse it, you don't obtain the full S curve back. But then if you take that backwards and reverse that, it's like another KL minimization, so another set of the IPF. And if you keep doing that and doing that, reversing and reversing, you force convergence in finite time. And the convergence is as close as possible to the Brownian motion, but fixing the marginals being a Gaussian and this S curve. So this is kind of the gist and the whole motivation.
I'm a little bit more interested in how you go. So you get the first iteration.
Yeah.
How does that feed into?
So you somehow want to do a time reversal of this forward diffusion as your next one, but starting from a fixed. So rather than starting from the noisy S, the PT, start from the prior Gaussian. Yeah. How you actually solve the time reversal is what I'm going to talk about next. It doesn't have a tractable closed form.
So I guess I get so the third line, I guess.
Oh, the third line is taking this revert diffusion, reversing that again. So
You reverse the back one.
reverse the backwards to get a new forward. So keep reversing, reversing. Yeah. So in this next one, you sample from the S curve from the data, reverse that, or reverse backward, starting from the new data, and keep iterating that. So I'm only showing the first two, but this essentially is after 5 sequences of this. Yeah.
Okay.
Yeah.
The first line is you take the target and you blur it.
Yeah, you add some you apply Brownian motion initialized from that point. Yeah.
Okay. And you get blurriness.
Yeah.
Then the second line
Is you
start from the right, from the
Yeah, you start from the right, so you start sampling from a Gaussian, and you want to reverse it forward. I'll talk about how to reverse the forward in a second, but this is
So you estimate like a map or something from the forward and use it to.
So you take the this diffusion, take this diffusion, and you learn another diffusion which reverses this. Essentially, it's the KL minimization that I talked about in the previous slide.
Okay. And you get to something that looks like the center.
And it still hasn't converged. So basically, this has only gone to the center. So the center only comes back to the center.
Okay. And what I'm confused about is the third.
And then you ignore this.
Yeah.
Sample from the data again. So you fix the marginal. So this is equivalent to fixing the marginal. but solving the KL minimization. And this forward is minimizing this backward. So there's two steps. So you sample from one of the marginals and then take the previous diffusion and reverse it.
Sample from the marginal. You take the previous diffusion and reverse it with every step.
Yeah. So, so each step you fix the marginal and you reverse the diffusion from the previous one. So this is the fixing the marginal, and this is the reversing the diffusion given the previous. And it turns out that reversing the diffusion is the KL minimization. Okay, so
If we're assuming that, like, so the Gaussian we can obviously sample from.
Yeah.
How do we fix the target where we don't know?
so we're assuming we can sample from the data, so we have some data distribution, just samples of data distribution. I'm going to talk about a bit later. I'll kind of rush through a bit more that you can have two different data sets. But first, it's just a simple case of defining the forward process to conversion to Gaussian.
To simulate diffusion bridges, Brownian bridges.
So not in this case, but there's some recent work in the last 2 weeks which essentially replicates this, but using Brownian bridges, and it's a bit simpler.
Quantify the rate at which you converge the target in terms of T and the number of iterations.
Yes. So I think that I've not included it in the slides, but I think it's been the results are better now anyway. But
So I guess the hope, right, is somehow even though you have to do this several times, it would still be better than running a diffusion constant.
yeah, well, I guess if you run a diffusion for a long time, it's going to be slow at sampling time. This is slow at training time, but faster at sampling time because you have better reverse diffusion. But there's a theorem which Valentine proves, which is that if your this is if your drift of your diffusion is close to the true one, then your generated data is close to the true data. And this is in terms of how well you fit your diffusion, the discretization of your diffusion, which is this gamma t, the time, which is okay. This exponential is what's been removed in the latest work. So this is your discretization term. So this is discretization term, and this is your mixing of your forward process term. But I've not included this because I think there's been like 5 or 6 different works recently which have got much better results, much theoretical results. But I guess just to reiterate the reverse diffusion notion. So you have an image like a dog, which is actually Yang Song's own dog. You take the image and noise it through each pixel independently through some SDE, this forward SDE. So you go from XZ, X0 to XT. So it's a forward noising process. And then the reverse diffusion consists of sampling from a prior, so this PT, so this would be a Gaussian, and then running this reverse diffusion, this backward generative process. And what you notice is that the backward process here is not just the negative of the forward in terms of the drift. So this is actually negative time, so it's not very nice, but essentially this should be negative. If you flip this round, this will be negative f plus this Scotland. But here they've just I've just copied this, it's negative time. So this Scotland is intractable. So if you can approximate this, and the theorem I showed before, if you can approximate it well, then your diffusion should be good basically, and you should recover your true path. Okay, and that's the whole case now, is to approximate this score term, and then essentially do that repeatedly. So this is very popular. So because it works in high dimension, and I guess you've probably seen these text to image models and everything, this is the same idea behind all of those. So OpenAI are quite big on this, and image editing and all this kind of stuff, and audio generation. So also what's interesting is not really dependent on just images. It can be used for almost any data modality. Okay, so this KL projection term I talked about is equivalent to the time reversal. Okay. So again, if you just decompose by this disintegration idea, that you can split your KL in terms of the first marginal, which is fixed, and then the rest of the path. And the rest of the path can be decomposed into the time reversal. So just literally the Bayes rule. And this partition shows like this is going to minimize the KL. So essentially you're sampling from the marginal and then just reversing the previous diffusion. And this can be done in continuous time, and it's in the paper in continuous time. It's just easier to explain in discrete, at least for me. Okay, so that's the basic gist. And where does the score term come into this? So you choose the forward to be a discretization of a continuous time STE. Apply Bayes rule, and if you take the times, like the discretization time gamma to be small, it turns out this means take the ratio of these two, take the exponential log of the difference between these two densities, form a Taylor expansion, you get this. So just trust me. And this is kind of in a very informal derivation, and you can make this more formal in terms of generators and things. But this is roughly giving you an idea. Essentially, it's using Bayes basically. So it's actually not too complicated. Okay, so how do you actually approximate this now in a tractable way? So this is actually extremely scalable to approximate this. Yeah, so use the Fisher identity here, and how does that come up? So this can be derived by this whole log derivative trick, which is super common in particle filtering in various different fields. So I'm sure everyone's quite familiar, but if not, essentially it's the derivative of log can be expanded as analytic. Expand this with S, so condition on some previous time in S, so S less than T. And repeatedly apply this log derivative trick. I think I've got, yeah. So take this and substitute that again. You notice some cancellations. So the two density terms cancel, and you get this expectation. Okay. After that, the conditional expectation is the same thing as the minimizer of the L2 loss. So this is like the definition of regression, or definition of conditional expectation, one of the definitions. So this conditional can be written as this, and then learn essentially parameterize some function s theta, which takes in time and position, and learn the score. I guess you could have one function for each time point, which is what people did a couple of years ago, but it turns out it's much easier to have a function which takes in the whole time and learn the whole score function across both time and space. Yeah.
Expectation with respect.
So this objective is for every t time point t, and so to train you can just sample any t independently. So what's quite nice is that you don't have to differentiate. So say you're learning this S theta with a neural network and you want to use great percent, you don't have to differentiate through time anywhere. You just have to be able to sample xt, which for Brownian motion is easy, and compute this conditional density of log graph log conditional density, which is easy for Brownian motion. So that's kind of nice. So this is super scalable. You don't have to backprop through t at time, like continuous time normalizing flow, for example. And what's interesting is that this is actually consistent in the sense that this will minimize this. So it's just, yeah. So one way of thinking about this is taking a complicated problem, splitting it up into many, many smaller problems which are deterministic. And if people are interested, so if you properly train a score network, you can show that it's actually conservative. And by conservative, I mean it is actually a gradient of something. And how do you measure this? It's in terms of, well, I guess 2D, it's like take the Jacobian of, which I guess the Jacobian of this function s theta in terms of x and see if it's symmetric. And that if it's symmetric, then it's you can prove that it's a gradient basically. So it's like the like taking the second derivative and swapping the two what you're taking gradients with respect to. Okay, so that's the basic training procedure if you like. So you sample a time point t, run the diffusion up to xt or to that enclosed form for Brownian motion, compute this loss, learn this s theta, plug this s theta back in to reverse your diffusion, and then you have a reverse diffusion. For context, for high dimensional images, well, like CPAR10 will take a couple of hours, like a 32 by 32 by 3. 2-dimensional setting, this will take 5 seconds or something, so it's fairly quick, but that's low dimension. 50-dimension, it might take, I don't know, 5 minutes. MNIST 28 by 28 by 1, it takes about 10 minutes, 15 minutes to train. And this is without any sort of, meta learning or amortization or something, so it's fairly quick. It's on a single GPU. For the 2D, it's just on a CPU. For CPAR10, it's a bit more complicated, and it's on again, I think 5 hours and 1 GPU, so it's quite slow. But I guess people can scale this to massive data sets and computational resources. So the text-to-image models, which you see trained on the whole of the internet, take, I think it's like a week or 2 to train. But that's using thousands of GPUs.
So if you like don't care about images,
Yeah.
let's just have like data,
Yeah.
like I learn a posterior person.
Yeah, so actually you can so some work by Yu Yang on conditional Schrodinger bridges don't use neural networks. They use they have a basis and they just learn the weights of a basis of functions, right? And they parameterize their score in that way for low dimensional problems for filtering. So they run a Schrodinger bridge at every step in filtering to run transport. And there's a connection between transport and the Bayesian updates basically.
Can you actually?
Yeah. I don't think it's there's probably better ways. It's good for I think it's good for simulation-based inference where you don't have a density of your likelihood and somehow able to run Bayesian inference without the likelihood. I can't remember the exact details, but this is my understanding. But it's just like any transport really. So if you can, so it's a bit of a weird one, right? So this is not as fast as Synchron or as training a transport map in low dimension, but those methods don't really scale to high dimension, and this does. So it's like if you want to use it on low dimension, maybe the other methods are better anyway. Maybe there's a sweet spot between high dimension and complicated problems.
So in the super algorithms plan, I think it's worth doing something like this versus when it would not be worth doing.
Yeah, so here you have a continuous distribution, which you would look interested in. Anything beyond like, I don't know, 10 dimensions, Synchron's not going to be great. I don't really trust these parameterizing transport maps. So anything like moderately high dimensional, this is probably better. So maybe above 20 or something.
In like the inference, it's competitive with like other machine learning type models, so even in low dimensions. It's like over stuff. We have some work on this, and it does like pretty well.
Okay, nice.
Comment on training a bit more. So you said split the problem into many smaller versions.
Yeah.
That would be T.
So yeah, exactly. So you take the whole, slice it according to T.
Wouldn't you want to kind of smoothing that goes on over T? Because in principle, you've got some Dirac methods, like, you can do this exactly, you just say,
Yeah. So yeah, I think the smoothness comes from the network parameterization of S theta. So you take into account T, typically like the people use positional embeddings for T, and that gives it sort of continuity.
Higher than like past 10.
This is good, yeah, compared to Synchron. I don't think Synchron's, like I said, Synchron is discrete. Synchron for discrete approximating continuous isn't great. Synchron for just discrete is good. if that makes sense. Yeah. So yeah, we I think we overfitted to MNIST when we were doing these because I didn't have much. So we got it spot on. And so for MNIST, we managed to get it into so this was 2 years ago where diffusions weren't great when we did this. And so people were using 1,000 time steps, and we managed to get it done in 10 time steps or 10 discretizations. So it's a lot better than what it was, but nowadays it's improved significantly based on lots of hacky stuff. So say your grad log is intractable from time 0 to time t. It's equivalent to, I mentioned before, any s or here u was less than t. So if you can simulate up to time u and have this conditional log density, then this is the same. So that was the original proof, was any time s less than t, or here u less than t. Also, without a discretization, so in continuous time, rather than learning the score, you can learn the whole drift, which is the negative drift of the previous one plus the score. And this can be done in continuous time, but then using a divergence of your drift, your backward drift. So here's the F is the forward, B is the backward that you're learning. And this is called implicit score matching. The divergence is hard to compute in high dimension. People use these Hutchinson's trace estimator, Skilling trace estimators and things, which seem to work reasonably well. So for the higher, so for the first IPF, you can use regular score matching. For the second IPF step, you're reversing a neural network parameterized diffusion. So the drift of your network is the drift of your diffusion is a neural network. So you can't, it's very difficult to do this. So you have to use this. And that's the biggest weakness because it's very slow. You have to simulate your diffusion up to time t. That involves running multiple neural network evaluations to train the network. So it's not the best.
So I guess right now a hyperparameter is like T, capital T.
Yeah.
And also like I guess you have to discretize as well.
Yeah, so the discretization schedule, so you can rescale your diffusion by this GT essentially. And it will involve timesing your drift by GT and timesing the volatility term by root GT. People choose these schedules like out of the air. There's not really an awful lot of work on how to learn the proper one or what an optimal one in some settings. For an OU process, you have the closed form Marshall. Essentially, it's a linear combination of the target mean you want and where you start from. So I guess you could optimize the schedule, advertising the schedule with a basis of increasing functions or something.
How sensitive capital T in the schedule?
So people have been trying to reduce them, but yeah, it is very important. So what's actually the most sensitive part is the discretization close to time 0, close to your data. You have to get that quite good. Like people have some crazy results whereby they essentially run your diffusion for your target is nowhere near Gaussian. It's like a Gaussian but with standard deviation 50, and what you're sampling from in the reverse is a Gaussian with standard Gaussian. It seems to work, but what we found is that you don't really recover the true data sets unless your marginal coincides with your prior, which is what's enforced in the Schrodinger bridge setting as opposed to regular diffusions. So a regular first, like just a single time reversal is what I call a regular diffusion, and the Schrodinger bridge is the iterative. If you have a huge time, then the two coincide. The regular diffusion and the Schrodinger bridge will be the same. But there's all sorts of tricks people do. Actually, one thing that's quite nice is that you can, based on the score, you can run like an unadjusted Langevin in between. So it has a corrector step in between your sampling of your diffusion. So you say you sample a long time, then at each time point you can correct it by running some Langevin. And so there's a lot of connections to MCMC here. You don't have the density at time t for the reverse diffusion, but you do have the score. There's some ways to get density actually. We'll talk about it later. So yeah, this is the basic gist. And so when I mentioned this, it's essentially iterating these KL minimizations, but with drift matching or essentially with a diffusion. And so you have two drift networks, one for forward, one for backward. I'm going to skip over this in the interest of time. This is just practically speaking of why you parameterize the drift and not the score, because if you parameterize the score, after k steps, you have k different score terms, or 2k score terms. So this is just an implementation detail. So this is the actual algorithm. So each of these blocks is a KL minimization, so a gradient update step. And the expensive part, which is where things really need to improve, is actually simulating the diffusion at each training step. So we introduced some tricks to get around this. Simulate the diffusion, cache it, run some MCMC. You have a much wider training data set rather than having to simulate at every time point. Yeah, exactly. Yeah. But yeah, it's not super scalable as opposed to the closed form. The initial reverse diffusion is much more scalable. So yeah, the initial process, we forced convergence. So one of the motivations that we came up with was to run the diffusion in a smaller number of time steps. So like at the time, people were using 1,000 steps and we got it down to 10. But nowadays, like with distillation. Yeah, so discretization. So we essentially in your initial forward diffusion, it's fixed forward. Here we're learning the forward and the backward to get a good forward that will converge faster. So essentially, it's like your diffusion could be too long or too short. Here it's making it just right, and essentially your trajectories become straighter. So yeah, if it doesn't converge, the forward doesn't converge, the backward doesn't converge. So we make it converge by using this iterative process. Yeah, diagram again. We showed it for some simple steps. So here, yeah, I'm this for 12 steps. I think this is not very good results for Celeb A, but dimension 64 squared. We didn't really have much compute at the time. Yeah, it works reasonably well. And this is only 50 time steps, whereas I guess at that time people were using 1,000 or 500. Yeah, exactly. The still works a lot better. I'm hoping with some extra computes. So this is complementary though. So this is a form of distillation. You're training a network and using that as a teacher to train your next network. The progressive distillation just essentially takes your diffusion, converts it to an ODE or like a deterministic sample, and then tries to overfit a neural network to make it smaller, basically, but in discrete time. Whereas this is continuous. In theory, you can take your trained model and distill it deterministically using progressive distillation, and that will get you a bit better. But these are all very expensive, and you only really do distillation if your model's perfect. And it's not. At least for MNIST, it's good. And so because the forward process does not need to converge, you can go from image to image. So this is like 2D to 2D or MNIST to EMNIST. By that, essentially at each IPF step, rather than sampling from a Gaussian, you sample from another data set. I guess you kind of hope that your first forward process is close to your other data set to make it work, but it doesn't need to be. That's the whole point. So I've not noticed any mode collapse from diffusion models. So I can show some examples of like a Gaussian grid where you have like 50 Gaussians, and it seems to cover all the modes. For MNIST, for example, oh yeah, I don't have the plots to show. So we converted the MNIST to like a 2D, like a overfitted a VAE to it, and so we could plot the 2D representation of MNIST. And we noticed in the first IPF, essentially you cover the mean of the data set, and as you progressively run your IPF iterations, it covers the whole data set. So yeah, it seems we've not noticed any problems really. It's hard to know, but people run this on images a lot. It's hard to know whether that's just quite easy to run all the networks that overfit into images. So I'd be interested in knowing any sort of more complicated things people can run this on. But the theoretical results that we got, or Valentine derived, was that it should cover the true data set distribution. And if you don't have enough data, it will overfit and recover your data set. So if those theories are right, and that if your score is trained well enough, you shouldn't really suffer from mode collapse. So yeah, these are the interpolations. In terms of OT, so these are using very small networks. So I say small, it's like 100,000 parameters, but not like billions of parameters. And we recover between 50-dimensional Gaussians, recovers the true transport coupling. Not for us, this is like a very, very small network. I think it was like 50,000, doesn't really do very well. So it needs to reach a certain size, 100,000. Oh yeah, sure. This is the number of IPF steps. So as you train your running a bridge, this should essentially converge to the true. This is the theoretical value that it should be getting, and the error is the y-axis, or the actual values. Yeah. So this is using a small network. So oh, and it's not very many. So for each IPF step, you have to have no number of training iterations. This is where the training wasn't complete. So this was 10K training steps. This was 20K. This was 50K training steps. So you need to converge basically at each step.
So with a large number of training, a lot of
Exactly, yeah. And yeah, you really need to converge in your training steps per IPF step.
so again. Still right behind maybe
Yeah.
in your experience, like what matters more, the quality of the training or the number of iterations? Quality of iterations, but smaller or like.
Yeah, so I think that quality is probably important to me. Yeah, I mean, it depends on what you want. Like if you have your forward reference diffusion with a very large diffusion time, integrated diffusion time, then you don't really need many IPF steps. Your along diffusion, the first iteration will converge. If you want a very tight diffusion and really force it to be within fixed marginals and a low number of time steps or low amount of time, then you need lots of IPF steps. And there's a trade-off here between, because you're training networks at each step, you can accumulate errors if you're not careful. So it's far from being a complete procedure. It still needs a lot of work. And yeah, there is a likelihood computation idea. So for every SDE, you can compute have a corresponding ODE, and hence you can use a normalizing flow, a continuous time normalizing flow, and compute likelihoods from data. So it's similar to a score-based generative model or a Schrodinger bridge. In a score-based generative model, essentially it's just the first reference diffusion. If it doesn't converge, this is actually not true. So I think the first person to publish this was actually wrong. They said it was exact, but it wasn't. Because they didn't actually converge, whereas the Schrodinger bridge forces convergence. Or they kind of hope it converges, shall we say. Maybe it does, maybe it doesn't, who knows.
Converge here is the IP species.
Yeah, exactly. Because if that is not the case, then this is wrong, right? You need to be, so using exact likelihood is a bit of a stretch, in my opinion.
Sorry, what you said. The convergence here is that when you run the forward process where it lets a time sheet is where you prescribe that it's going to.
So essentially, this is mapping data using a normalizing flow or continuous time normalizing flow back to a Gaussian, and then looking at the Gaussian, for each data point, looking at the Gaussian and computing a likelihood. If your forward diffusion doesn't converge to the Gaussian, then looking at the back, like looking at the ODE and the value to the likelihood Gaussian is a bit disjointed from what your flow is doing. So it's not really a good evaluation. I'm probably not going to go over this. Yeah, I've got half an hour. Okay, I'll be very quick. So this setting expands to not just Euclidean space, but to the Riemannians. This is what we did last year. So essentially everything that we did for the Euclidean setting can be expanded to the Riemannian setting. There's less closed form solutions, and there's a few extra constraints that you need. So the forward noising process, well, would be a Brownian motion in the Euclidean setting. In the Riemannian setting, it's a manifold Brownian motion. So this is a compact manifold in general that we're talking about here. And so a geodesic random walk, which I'll talk about, essentially it's, I think I've got an algorithm somewhere. Essentially it's running Euler-Mariano steps in the tangent space, projecting back onto your manifold using the exponential map. And this, if you do this for Brownian motion, so there's zero drift here, you'll eventually, rather than like an OU process converting to a Gaussian in this manifold setting, you'll convert to the uniform across the manifold, a compact manifold. So when you're in your time reversal, you sample from the uniform on the manifold itself, rather than sampling from a Gaussian. So these are the two big differences. And this is the diagram I have in my mind when I think about this. It's just a tangent. This red line is running the step on the tangent space plane, and the exponential map is pulling it back down to your manifold itself. Again, because the density on a manifold is not typically available like in the Euclidean setting. Maybe for a sphere it's fine, for a torus it's fine, but anything more complicated it's not. And so you have to resolve to this simulated loss function, this ISM loss, implicit score matching loss. So similar to the Schrodinger bridge. And again, so the prior, it's not a Gaussian like I mentioned, it's this uniform on the manifold. And this is roughly what you get. So this is the reverse from going from uniform to a von Mises-Fisher distribution.
So the circle or?
Oh, this is sphere. Yeah. Yeah, so this is the ISM loss. So the exact same procedure works for Schrodinger bridge as it does for Riemannian score strength modeling. So everything follows through basically. The Kale minimization time reversals follow through. The parameterizing the neural network in the tangent space, I guess, needs a bit of a trick. You need to be able to parameterize your network for the tangent space, and running your diffusion on the tangent space again. But there's not like all the components. There's an equivalent component for the Riemannian setting, so it's almost identical. And so yeah, just some toy examples and spheres from the spherical harmonics. It seems to work. And just from one pole to another pole, or one side to another side, you get a nice interpolation. So for some more realistic settings, we looked at earthquake data and fire data and flood data and stuff like this. So I think this is example on earthquake data. So you have samples on the sphere from earthquakes or something. I want to generate new samples, and we want to do this in a very small number of steps. So this is 10 time steps, so discretization to 10. And regular Riemannian score-based structure modeling doesn't converge in 10 steps, so the samples aren't very good. The green dots are generated samples, the red are true observation. But for the Riemannian setting, by doing this IPF, you manage to converge quickly, and so in 10 steps, it's all good.
Exactly.
So again, it's the same IPF procedure. Oh, here we're just generating likely spots of earthquakes.
Actually, that actually happened really big.
Well, actually, I think these are the I think these are fault lines. But yeah, it's not. I don't think it's super useful. Because like if you've already well, it's like a density estimation basically. I think what's more useful would be for robotic interpolation on a manifold of robotics arms, or molecule generation. Essentially, people use these diffusions, Riemannian diffusion, essentially. And people trying to generate lots and lots of test molecules. And if each one takes a large amount of time, like you're generating millions and millions, it's not ideal. Whereas, so I suppose this acceleration is good. So this is the main use case, is the acceleration of your diffusion.
Right.
Yeah, they do a lot of this kind of stuff. Yeah, I've never really got into the molecule game, but I think you need you need some subject matter expertise because it's
Actually, like to discover
I think maybe one or two, but like for the amount of money being funneled into it, it's not a great return. Like well, maybe there's more I just don't know about. But I guess it could be very useful if it starts to yield something. But each new drug is billions. What other things? Yeah, and I guess the Riemannian setting, you don't really have the same acceleration techniques as you have in the Euclidean setting. So like distillation and things, I don't think transfer over so easily. Or these implicit diffusions whereby you predict time zero at every time step. That's kind of tricky in this Riemannian setting. Because you have to make sure it's on the manifold. I think that's pretty much it then. So yeah, that's the presentation. Yeah, sure. Yeah. So typically you have take your image text pairs, and they use some encoder for the text, so you have a vector something. You take your image, you noise it, then when you are training your score, you're putting your objective in your score function, you just input your text vector as well as the noised image, and that's kind of it really. But they don't predict the score, they predict time zero or x zero. So I guess there's a connection here between the score and the denoised x zero. So the expectation condition on time t will be something like so x zero, like the prediction will be the expected x zero given xt, and that works out to be xt minus the score, I think, or something along those lines.
Like, I guess, like, practically, I initialize it, like, testing, how does the diffusion go towards the sample that I wanted to generate versus just any sample?
Yeah, because I guess you conditioned on the your score to be on this text.
Yeah, but I guess, like, we didn't learn the conditional.
Yeah, you do, because you condition you input the caption or the vector of words into your score when you're training it. So I guess it kind of overfits to the so I guess at time very close to Gaussian, it isn't very informative, but as your image starts to emerge, then the text conditioning is more important.
That's like when value something, it's actually doing training. Like,
No. So like during the training, you have this let me find it. So let's say this loss here. Rather than just putting in t next t, you have another input, your text caption. And then at deployment time, you just condition on you input your text caption as well. Because there's like your text caption matches the next t next zero. Yes, typically this can be for a linear diffusion. This can be reparameterized to not predict the score, but predict the at time zero.
so they're actually like creating a density as across all possible words they can generate.
So they're essentially amortizing this across the vocabulary. Yeah. Is that kind of crazy?
That's just a week.
Yeah, I think it's like, oh yeah, I think these models are shrinking quickly. I think it's a week or two. But I guess they use thousands of GPUs. It's a lot cheaper. These models are a lot smaller than like these ChatGPT things, which take months to train.
What's the scale of something like you realize if you
So you can probably do like C-bar10 and things, yeah. Yeah. I think there's a library called diffusers by Hugging Face, and they have these like latent diffusion models. So people here essentially map their data into a low dimensional space and train on that space. The dimension of your diffusion is really important. Like dimension of the states that you're running your diffusion in is important because these are it's expensive memory wise, and the loss here is actually quite high variance. So you need a large batch size.
you speak of it, but like what people like us can do in this world?
So I think there's a lot of connection here between Monte Carlo and this really. So like one way of conditioning your diffusion is to through like an SMC type approach, So essentially in your reverse process, you could have weighting based on observations, or even no one's really looked at it yet, but I guess you could do resampling or something. So yeah, I think there's a strong connection here between. I think recently people tried to use HMC for the corrector steps. So every time you run a step of your diffusion, you run some MCMC at the same time. I don't think people have really got nailed down the time schedule. So I mentioned this before about what's the optimal time schedule or the discretization. And this seems like a bit like a tempering problem in some ways. You're essentially putting, you're rescaling the diffusion by some time schedule. And if you put your the coefficient in front of here, it's like putting coefficients in the exponent in here. So it's a bit like tempering. So all these things are a bit like people do it heuristically. It'd be nice to have some more better results really. Other things. So expanding it to Riemannian settings is quite mathematical. I suppose that's been done now. There's still, I guess, still open questions about the convergence rates. Why does it work so well in high dimension? It's not really clear. Yeah, so I guess there's still quite a lot to be done.
Your experience with so you mentioned briefly the backward process, you can kind of turn it into an ODE, right?
Yeah. Yeah.
What's your experience with how that compares to standards?
Yeah, so I was I think so NVIDIA have this paper elucidating diffusions or something, and I think they use a deterministic sampler and it seems to work quite well. But from my experience, I don't think it was as good. I think the noise somehow helps. And there's been, I think, a few papers recently where they show that noise theoretically helps as well. So I think, I can't remember exactly what. I think like for training, the variance is reduced. And for sampling, I think there's also benefits, but I need to dig up the papers. So I guess there's this ongoing debate about like flow matching versus diffusions. And they're almost the same. And I suspect the diffusion is somehow a bit more robust.
So with neural networks, I think there is this way to see a neural network as a diffusion process when you model the difference between units.
Okay.
And then you can write down the full equation and it looks like a diffusion process.
Right.
And then there is this connection. So people, I think they're trying to learn the parameters of the neural networks in order to match the final points. So creating sort of diffusion bridges.
Okay.
Is there any connection with diffusion bridges?
Yeah, so I don't really know much about that, if I'm honest. Yeah, perhaps, but yeah, I just don't know the literature very well.
And the other comment, so I think in computational statistics, people are interested to use Monte Carlo methods to simulate diffusion bridges. Is there any? Could be useful.
Yeah, let me. There's a paper we worked on with Jeremy. Essentially, it can be done. Actually, I need to finish this off. But essentially, yeah, if you have points, so rather than running from like a data set to another data set, if you just have fixed points,
There will be images, right?
images or I think here we use like some stochastic volatility model and some single cell dynamics. Yeah. But we need to find some better experiments. That's why I'm not finished. Essentially, you run your diffusion
Condition to meet.
from the starting points. The first forward isn't conditioned to hit, but the backward is starting from fixed points. And if you reverse that from starting from the original points, then that you obtain the original points. So that solves essentially it's the Schrodinger bridge, but in 2 directs, and it converges in one step. It turns out this is the something called a H transform. And it's equivalent to a grounding bridge and everything. And this can be used for simulating. I think it can be used for like proposals and things for simulating diffusion bridges.
Okay.
So I think we looked at the as a proposal and looked at the effective sample size and things like this. But the experiments were all very toyish. So we need to actually, I'm working on this right now to improve it.
How long do people train with the least squares loss, basically?
Yeah, least squares is probably most scalable, as opposed to the ISM thing, or like taking gradients all the way through time is just not scalable at all. Yeah, and ISM, you have this divergence term, which is tricky to compute.
And whether there's other sort of data types where the, you know, because essentially you're replacing a likelihood method by reducing it to regression.
Yeah, yeah.
There are other cases where you can reduce it to something else, sort of as simple as the least squares problem.
Yeah, it's a good question. I imagine so. So I imagine for optimal transport, this is similar, I guess. So in the dynamic formulation of transport, I imagine there's an equivalent. Well, there's this. But maybe for barocentric interpolation, maybe there's an equivalent format whereby you sample in the simplex of weights of the barycenter, and perhaps there's it's not going to be a least squares, it's going to be a involve the potentials basically, an OT problem. But it's similar, you're breaking down a complicated problem into many small ones, which are all kind of related. Some are easier than some are harder. And so essentially you're leveraging the easy problems to make the harder problems easier. I think, yeah, people refer to this as iterative refinement. I think people are trying to use this for like text and stuff now as well. So there's been not much progress or not much success.
About wanting to do these polls. So for me, it's easier to think about the control frequency stuff because
Yeah.
It's like if you were doing this on a model which is a binary graphical model or something, it's versus whether in some way, you know, doing the backward process reduces you to putting a bunch of code to super graphics.
Maybe.
This would be one of the things I like so much about it. Just reduce it to least flow.
Yeah.
I mean, don't do it to the extent that it's solving a complex problem anymore. So it's like how morally many things become very nice.
Yeah. And I think there's some results that suggest actually that you will obtain the actual score if you train for long enough and your model has enough capacity and everything. So it's like consistent in that respect. Yeah, I'm interested in other like I think the images stuff it looks good, but it's not super interesting. It's just a lot of compute thrown at the same problems. I think there's a lot of opportunity in discrete space. So Andrew Campbell, people have been working on discretes. And it's not super satisfying just yet, but I think there's a lot of interesting work to be done there. For other settings. So for OCE, I guess you can try and use the Schrodinger bridge for barycenters. I don't really know what people use barycenters for, but it seems to be a common problem. For birth-death processes, I guess do a diffusion with time reversal for birth-death seems maybe has some use cases in single-cell genomics where things die. Yeah, I think there's other, like making non-linear diffusions more scalable. I think that's a good area for computational stats people.
Doing some sort of control SIR stuff.
Yeah, exactly. Yeah. So I was trying to make this Schrodinger bridge stuff. So interesting using different modalities. So I tried working on like generating stochastic processes and things. So I was working with like NVIDIA for the last 6 months on something like this. Hopefully it'll be finished soon. For like 3D shapes and 3D shape interpolation using diffusions. But yeah, I think the field is moving super quickly, so there's new papers on this every day. What other things? I'm kind of interested in, like I said, learning the some more fundamental problems about how to learn the actual time schedule, or like the discretization schedule and things like this, empirically as well as theoretically. I think there's a big gap in terms of generalization, how like diffusion seems to generalize, but what does that mean? How do you quantify this? It would be nice to see that as well.
There are a lot of, like outside of like, I guess, Valentin and Arnold's group, like, are there many people that Comstats were looking on this?
Who's working on it? So, but the problem is a lot of these models are very big, so it's like you need compute resources. So I think Oxford, I guess because we were quite early, there's a lot of expertise there. Well, for now. Who else is working on this stuff? I think some people in Durham are working on this. A lot of people at MIT are working on this for proteins. I guess Stefano Ehrman, he's like one of the leaders in this. For like, I think he's working a lot on these inverse problems using diffusion, so in painting and this kind of stuff. And the pure stats, I think it's quite limited actually.
Like 10 minutes for MS doesn't seem that long.
No, we've got it super quick, but I think it's.
Do you think this could be used for like even small scale like
So that's what I'll be interested in doing that, but I think it needs to somehow amortize the problem or something because training, yeah, it's not like for a lot of OT problems you can take a gradient through it. So this you have to take a gradient through the training is seems a bit unreasonable. So yeah, I'm not so sure. It'd be interesting. Yeah, that's it.
All right.
Cool. Cheers.
Yes,
Mm.
thank you. Thanks for the speakers, for the participants, for the organizers, who helped me, the secretary, the grant, the sponsors, and everybody. We have lunch with pizza upstairs in the common room. Yes. Thank you, Sebastian.
Oh, yeah.
The thing people do, right?
Yeah, well, 10 or 15 minutes, something like this, yeah.
Or just to generate like fakes.
Yeah, so it's generous. Well, as in not for the training, not the generation.
Yeah, no, of course. I just don't know what to think of. Just think fucking around. So, but I actually have no idea what it is.
Oh, yeah.
They have like